Today's lesson is we're going to put a little bit of our Chapter 2 vector discussion into all of the kinematics that we've learned. All the distance, velocity, time, acceleration, all of those things, because a lot of them are vectors, and so they follow all the rules of vectors that we did, I guess, a few weeks ago now. But they also have a lot of things that make things simple with vectors. You have to account for both dimensions, but we can do different things. So this basically allows us to do turns, which is a little fun. We've been having to make up all of our examples and all of our situations all have involved things that just go forwards and backwards, and they're not allowed to turn or curve or in any way, which is weird because things in our world turn and curve, and so we have to be able to do math on things that don't just go in one direction, forward and backwards. So that's our main goal for today. And so basically I'm going to do a little bad drawing here really quick. So I'm basically just going to take a curve kind of like this. I'm going to draw it kind of like this. And I'm going to say it's a dotted line in the middle. I'm basically trying to draw a road here. I'm trying to do a really bad job of drawing a car. So I'm going to draw a car here to the best of my abilities, which is bad. And then I'm going to say the car is now over here. So this is what I'm trying to draw. Hopefully this makes some graphical sense where I have the car was here and now it's over there. And we can basically put this on an external kind of like grid. I can say that I have an X part and a Y part, and we can say that the car moved from here to here, and it took this path here. That's perfectly a straight line that I drew right there. And so even when I'm considering something like its displacement, it's going to have a certain amount of its displacement in the X direction and a certain amount of its displacement in the Y direction. So that's kind of what we're working with here. Now we're going to refresh our brains about all the things that we learned about vectors. And vectors are always independent of each other. Well, specifically, X motion and Y motion, because these two vectors are 90 degrees, or my favorite math word, orthogonal to each other. They are independent. So all the motion in the X direction can be considered separate from the other one. So separate. And one-dimensional. So if I only consider the X movement, all of the things that I've done in the previous chapter all work the same. They don't change. And then if I consider all the things in the Y direction, all of the things I've learned over the last chapter also apply exactly the same. Now our link between the two is our scalar that we use to measure everything else. What is the scalar that gets involved in most of the questions that we did? It's time. So time elapsed has the same value for both. So let me write this in. Time elapsed has the same value. So we can see how far it goes in the X direction. We can see how far it goes in the Y direction. But the time it takes to go from here to here is the same for the X direction as it is for the Y direction. The time it took to go wherever it was going is the same whether I'm measuring the X components of anything or the Y components of everything. So this allows us to go between the two symbols, basically the two different axes with time. Time goes with both. And that's a super important thing to remember. As you can see what I wrote on the board already, we use subscripts to show which direction we're considering. So these x's and the y's that I've drawn here are subscripts, just like we have VF and V naught. They're subscripts to describe what we're doing. They don't actually account for any math. We don't do math on any subscripts. They're labels, so we don't get confused halfway through a question. And specifically, when solving formulas, use only x or y in the subscripts. Now, I say this and I don't know if it's not a great sentence, but basically this is the sentence I really want you to remember. Do not mix x and y in the same formula. So if you're doing math on how far it went in the x direction, I can measure its speed in the x direction. I can measure its acceleration in the x direction. I cannot measure anything in the y direction. Its position in the y direction and its speed in the x direction are independent. One doesn't affect the other. They are not, you can't cross them. And so, like, when I use my equation examples here, is you can basically replace any of the vectors in any of the equations with all the same component, I think is the word I want to say there. So, like, for the formula, let's do this. VF in the x direction is equal to V naught in the x direction plus the acceleration in the x direction multiplied by time. I can, like, as long as it's a vector, all of the vectors have to have the same letter with them. I can't switch x and y in the same formula. The time is the same for both because time is a scalar, but I can't mix it. These are separate, right? If I write VFY equals V naught y plus a y and t. So these are two separate. We can't cross any of the values in them. And we can do this for any of the equations on the whole sheet. I'm not going to write them all out because they're just the same, but all the vectors have an x or a y with them. All the problems that I see in people solving these equations on their assignments, homeworks, or on tests and quizzes is they've put an x direction with a y speed, and those can't cross, and that will lead to mistakes happening through. Those measurements don't work together. So that's all the examples I'm probably going to spend time writing out right now. The book had a ton. All of your equations, not just the kinematics we've seen, all the ones that have forces in them, all the ones that have, well, energy doesn't count, we'll not worry about that yet. But any kinematics formulas that has vectors in them at all, if you keep all the letters consistent, then it's fine and true. If you mix the letters, it stops being true. That's the most common mistake you see in all these problems. Otherwise, everything's the same as it was last chapter. But if you mix the letters, it stops making sense. Okay. Refreshing the rules of vectors. So if I have two components in the x and y direction and I want to find their resultant, we can do the same things we learned in the last chapter. We can use Pythagorean theorem. Pythagorean theorem to find the magnitude of both the vectors. So if I have an x velocity and a y velocity, I can put them together to a together velocity. So I can do things like resultant is just vx squared plus vy squared all square rooted. So that's my resultant vector. I can do that there. And I can choose any vector for this maneuver. I can have my acceleration in the x direction plus the acceleration in the y direction square rooted and done that. I can find their combined acceleration. I can do that with their displacements. I'll say the word right. Displacement, velocity, and acceleration are the different ones that we can measure. Distances don't do that. Speeds don't do that because they're not vectors. So any vector, this works. And we remember, how do we find our angles to figure out what direction they're going? we tend to use inverse tan. To find an angle is usually tan minus 1, and it's always y divided by x. And as those of you, because you were doing the quiz 5 seconds ago, most of you have your formula sheet up in front of you. This is like, it's written on there. I wrote that it's y divided by x on there, so if you don't remember that. You can now see that's, as of this chapter, we're now using all of the kinematics formulas. You can see the sine and the cosine and the tangent all in there at the bottom of that little sheet. So we're getting into those now. A skier starts from rest and accelerates uniformly at 1.4 meters per second squared down a ski hill. The hill has an incline of 28 degrees with horizontal. The skier reaches the bottom of the hill. The elevation change was 160. So what we're going to do is label our diagram with as many of these facts as we can. So our elevation change here is 160 meters. We're going to have a downward acceleration here of 1.4 meters per second squared. We know my initial velocity is 0 meters per second. And I have a 28-degree angle there at the bottom. Okay. We can also, because I gave you the space here, it's often sometimes easy to write. F naught is equal to 0 meters per second, kind of like this. A is equal to 1.4 meters per second squared. And displacement might be 160 meters. Okay. Oops, that squared looks terrible. Let me clean that up. Squared. Okay. Do any of these numbers need to be in one direction only? One of them needs a label X or Y. Which one? The displacement. Which letter should I give it based on how I drew it? I'm going to give it Y because it looks like it's the up and down part of ours. So I'm going to make sure that gets labeled dy. The Y part of its displacement is 160. Is its overall displacement 160? No. The distance between here and here won't be 160. It'll be more than that because of a hypotenuse. But we just know the vertical change will be that. Does the A, is it its overall acceleration? Or is it its X or Y? It's an overall. It's the result of it. It's the down the hill actual where it went kind of movement. So it shouldn't get an X or a Y. If we want to be really careful and add all of our subscripts just so we don't forget, you can add an R because it's its overall resultant acceleration at that point. You can add an R if you want to be careful. Usually we just leave it blank. If it's not X or Y, we leave it blank. That's normally how we take care of that. All right, so we get to break out our trigonometric functions for the first part. We're going to do the horizontal and vertical components of the skier's acceleration. And so we're going to find horizontal, so that is A in the X direction. And so that's just going to be A times the cosine of the angle that I have. So all our big memories here. Oops, let's keep this on the screen where I can see it. There we go. So that's going to be 1.4 times cosine 28. Oh, I should do these. I don't have the numbers beside me. So 1.4 cosine 28. Make sure we're in degree mode. 1.24, I guess. And basically the same thing for y, but we're going to use the sine function. Getting all of our good trigonometry back up here. Okay, so do this. Oh, much less. I get 0.66. These are meters per second squared. Just so I keep them in the same realm. Oops, not 2. S squared. There we go. Squared is terrible over there. Lost the ability to draw the number 2. Okay. That's it for this part of the question. Choose either X or Y to work in based on the context given. So in our given context, should we work with X or Y in this question, try to find time? Why would I use Y, right? It's good. You know why? Right, because we have the displacement in Y. So because we know our displacement in Y, we should try to find time with the Y components. If we notice part D, if you look all the way to the bottom, that's our horizontal displacement to find, and we don't know that, so it's going to be hard to use all of our horizontal numbers to get that. Okay, so we're going to use the Y direction, and so I want to use, this lovely formula. So we're going to say use the Y direction. So it's going to be dy equals v naught yt plus half of a y t squared. Isn't that awful? So many letters. Just wait until we get to more momentum chapter in Physics 12, where we have the speed in the x direction before the collision and the speed in the x direction after the collision. There's so many letters. Moving on. What's great news about trying to solve this formula for time is our v naught term is 0. So that goes away. We don't need this because of our v naught term. So we can try to just rearrange this equation for time. So it's not terrible. So I don't have a lot of space here, so I'm just going to rearrange it in one step. T, not red, blue T's. T is equal to, it'll be 2dy over ay all square rooted. So that will be the rearrangement of this equation to solve for time. Now I can put the numbers in. I know my dy is going to be 2 times 160 all over ay, which is 0.66 all square rooted. So that's the calculator buttons pushing I'm doing there. And we're making sure we use our y distance with our y acceleration. If we're using both of those, everything will turn out fine. Let's see what I get in my calculator. 2 times 160 over 0.66 rooted 22. Cool. 22. Seconds. Cool. Yeah. What happened to the half? The half turned into this 2. So I multiplied this by 2, that got 2, then divided by ay, and then square rooted. Just go backwards through all your steps and you should get there. That I want the x velocity or the y velocity. Neither. So I want their together velocity, right? So I want both the x velocity and the y velocity at the end. So I have to do them together. Now the good news is that I have both the accelerations and both the times. So I just have to do basically the same equation twice and then do the Pythagoras steps. So because I have the acceleration both and I have the times for both, I can use the same equation. I can use VF in the x, we'll start with x, is just equal to V naught in the x direction plus AX and time. And the V naught term is 0, so I don't care about that. So this will just be AX, which is 1.24 times 22. It's the AX times the T, which will be 1.24 times 22. 27. Let's call it 28 for now because we're not finished. Meters per second. And we get to do basically the exact same thing for VF in the Y direction. We have V naught in the Y direction, which is also 0. Oops, that's not equals there. That's a plus. AY in T, which is 0.66 times 22. 0.66 times 22 is 14.52 meters per second here. So we have X direction speed, Y direction speed. And now we can put them together. All together speed is the X plus Y. Oops. And do VY. Both of them are square rooted. So we can do this number. Let's just write it all in here so you guys can see it. 27.28 squared plus 14.52 squared, all square rooted. Yeah, I gotta do that now. Squared plus 27.28 squared. Square rooted. All together, 30. Well, I guess it'd be 31 at the very end. That's what I think the very end one would be. Yeah, 39 is what I get, 30.9. So it'll round to 31 when I'm all done. That's pretty fast. That's a very fast skier. Yes? Okay, so after I should probably include downhill is important. I want to find what the dx is, how far in the x direction he has traveled. So there's several ways to do this. I can use one of the kinematics equations. I can use trigonometry to find the missing piece of this triangle. So if I go back up to the top here, I just need to know this is 160 and this is just a missing side of a triangle with 28 degrees in it. I can just do that math as well. Or I can do a speed and time to find a distance as well. So I think I'm just going to use the trigonometry part. That's actually probably the fastest and the easiest way to do it. It's just a tangent function is all I want to do here. So if I just redraw myself a triangle here, just as a reference, if I draw this, I can just do 160 x and 28 degrees. I can just draw this triangle and use my SOHCAHTOA to solve it. That's probably the fastest way to do that. I can use one of the kinematics equations. Once you get down to like C and D in one of these questions, there's often many correct paths to solving an equation because you've been filling out the situation with lots more numbers. There's many, many correct formulas to use because you just have more values as the lower and lower you get through the letters of a longer question. So I'm going to use this one. So this is, to put all my labels on here, whoopsies, opposite, adjacent, and so tan of 28 degrees is 160 over x. Yeah, and so then that would make x equal to 160 over tan 28. Yeah, that's how that will go. Great. 160 divided by the tangent of 28 degrees. 300 I get. Oh, 301, I guess. So that's 3. Let's just write it as the decimal comes out. 00916. That's plenty. So, ew, it's only 2 significant digit question. Ew, I hate when that works. I hate when that happens, when you get numbers that you're like, haha, 300, that's a good number. No, it's a bad number when you want two significant digits. So that's annoying. Let's put a label on that. That's dx is equal. So it's b3. Ew, I don't like that. I would have written 300 and been on with my day here, but according to this math, it does work out to be 300.9, so it'd be 301, which is just, I just want the 2. So 3 significant digits would be great. 301 would be fantastic. 2 sucks. I'm sorry. So that's that there.